Okay, so we're going to be moving on to our next module, which is going to deal with gear kinematic analysis and selection. So you're going to notice here that in our learning plan, I do have it broken up into two parts. Okay, so part one we'll be finishing up today, we'll be looking at, and then part two the next time we get together, and then our third day this week it'll be a lab time. You do have practice problems. And you're going to notice those right here. The practice problems that we're going to be doing, I believe we're going to do the first three today, and then we'll save the last four for the next time that we're together. We'll kind of see. We'll gauge the time. Maybe we'll get an extra one or two in here. And then you'll notice that we have some questions here. So a little bit different question this time. Make sure you answer these two things you learned in this module. Oh, it should say module 5. Let me edit that so that as long as I'm here. And then I'm interested in knowing as you look around, um, let's see, hold on, let me save this real quick. As you look around, I'd like you to identify three places where you see gears in your everyday life. Are the AutoCAD practice problems? Um, these are not AutoCAD problems for Module 10. Okay, so you don't have to worry about that. Okay, so just paper. You're welcome. You're welcome. Any other questions? Okay, all right. So these will be the practice problems, and they come right out of the book. We'll be going over each one of these examples. And oopsie, I didn't want to do that. And then you're going to notice that you also have an assignment. And the assignment number 5, there's quite a few problems here, but we'll discuss these and how far you can get. Today, once we're done with our lecture, we'll see, and then we'll add on the balance of them the next time we're together. But they'll be similar to the example problems that we do here in class for our lecture. So, what I am going to do is I am going to go over to our learning plan. And we are going to start by looking at the PowerPoint presentation. Scooch out here for a little bit. And we are going to be opening up our books to page 260. This is the beginning of chapter 10, and then we'll be focusing on this chapter for the balance of the module. Okay, so our objectives here in module number 5 and looking at gear analysis is to, first of all, identify, different types of gears. There are a number of different types out there, as I can imagine that you have, some experience with. But I want to be sure that you get a good idea of kind of the ones that you could potentially come across being, out in industry. So we're going to be looking at a couple different types of gears. We are going to focus in on and do our work on the most common type, which is a spur gear is the kind of gear, and we'll talk about the characteristics of those and how then those calculations, even if you do a different type of a gear, you'll be able to kind of pull a lot from the basics that we learn about spur gears. You're also going to learn here how to calculate center distance, and then we're going to use velocity ratios and trains to kind of round out when we start kind of, if you would, ganging these together, for specific purposes. So that'll make a little bit more sense as we go along. So in the beginning here, the function of gears, in general, is to transmit motion from one rotating shaft to another. And most often, we are going to be decreasing the speed from what would be an input source to a driven machine. Okay. Now, through that process, we're probably also going to change direction of the motion, just kind of inherent of when gears mesh. And then also, most often, we're going to increase the torque. So if we're decreasing the speed, that means we're going to be increasing the torque. But you can set up gear trains or gear transmission systems to be an increase in speed, but then that would mean that we're decreasing the torque. Okay. Now, very common, if you would, input sources or sources of the rotational motion that are feeding into the gear system is going to be like electric motors or gas powered motors. And as I said earlier, these are most often going to be situations where we're going to want to reduce that speed coming off of that input and then increasing the torque. So on page 260, if I go underneath my camera here at the bottom, they're showing us an application. I'm going to kind of zoom in here a little bit. They're showing us an application of what would be the feed rollers for a scanner or maybe a printer type of a situation. And you're going to notice down here, they're identifying an electric motor. Okay. Now, off of an electric motor, typically, like I said, the rotational speed is going to be quite fast. And a lot of times it's too fast to be usable for an application. So what we want to do is we want to slow this rotational speed. So on this center line, if you would, this would be rotating. And you'll notice that there's a gear on the end there, okay? It would then mesh with another gear. And in this case, you'll notice that as this rotates around, this smaller gear, which is called a pinion, and it engages with the larger gear, called a gear, it'll naturally slow the rotation of this second gear down because as this rotates around, it has to engage with each one of the teeth on the larger gear, and it's only going to get about here with one rotation. Okay. Then what's going to happen is it's going to continue around. So it's going to slow this second one down considerably, and it's going to match whatever the final function or the speed that we need for whatever the machine is, or the scanner in this case, is going to need to properly line up. And in this case, pull a document through or move the paper along. So that's going to be something that the designer will determine. What is the appropriate speed rotationally from the input, in this case, an electric motor, to what the output would be, which would be the feed rollers of this scanner. Okay. And that's going to be a different, application for, each, type of a system that we're going to be designing for. So let me go back over here. Now, there are many types of gears, and on the following page, on page 260, we're going to see a number of common ones that we would encounter when we're out in industry. So I'm going to go underneath our camera here. I'm going to pull this up this way. And here in figure 10.2, you're going to notice that we have a couple different types of applications here. So in this case, we have spur gears. Spur gears are what we're going to be looking at for the balance or the duration of this chapter. The reason being is they are the most popular type of gears that are out there used in industrial applications. And the concepts and the relationships that we learn here cross over into the other kinds. Now, over here, another way that we can transmit rotational motion is through friction rollers, as we see. Now, in this case, there's not teeth that are going to, kind of push past each other, but instead, it's going to use the friction of the surfaces there to do that. Now, in the friction rollers, although they're a valid way to move things along, the opportunity for them to slip or to, not rotate relative to one another is greater because there's not what we call positive engagement, like one tooth meshing down to intertwine with the next tooth. This has much more ability to kind of overcome maybe jams in a system, or if something gets real heavy, this can kind of maneuver past that and not slip. Okay, so gears are a really positive means of like kind of transmitting that motion and torque from one shaft to another. Now, over on the right-hand side, this is where we're going to see a lot of different types of gears. On the top here are our traditional spur gears, as I said, and we'll look more closely at the actual tooth profile, but basically it's a straight, what we call face, and it's the same profile over the entire length of that gear, okay? And then what happens is the same size tooth, but on a different size gear. So in this case, if we would count the teeth around the outside here, there's obviously more teeth around the larger gear than around the smaller gear. And this allows us to do that, what we call um, speed reductions from an input to an output gear. We're also going to notice that when we engage one gear to another, we're going to change the direction of rotation. So if we look, in this direction, for the orientation of these gears, if my driver is going in a clockwise direction, looking down the center line here, this would be clockwise. Notice that it changes the direction in an opposite direction, and it would be counterclockwise then for the mating gear. That's something to take into consideration as you design, the final function of the gear set. Do we want them going in the same direction, the input to the output, or do they need to be opposite? Now, another arrangement that we can do is like a rack and a pinion over on the right-hand side. A traditional set of gears, as we see here with a pinion, smaller gear, to a gear set that's engaging, is we're going to have rotational motion on each one of those, if you would, center lines. In this case, we have rotational motion on what would be the pinion, but then on the rack, it's going to be linear or translational motion. Okay, so input would be circular or rotational motion, and then output would be linear. So this is kind of a special case, but we still have the engagement of the teeth like we do on, rotational situations. Now, a couple others that we see here as we go down below, you're going to notice that we have spur gears, but in this case, instead of having engagement on the outside of the gear, we have what we call an internal gear arrangement. And that's just where the pinion rides on the inside of a gear as opposed to the outside peripheral or the outside perimeter of that gear set. The next one that we see here, these are called helical gears. If you look closely, the helical gears have the teeth, instead of being straight across or perpendicular or parallel to the center line, they're at a little bit of an angle. Okay, so if we just kind of compare spur gear to helical, you see this angle occur. Now, the reason for that is you actually get more surface area contact across there because of the nature of the diagonal, okay? And what that benefits is number one, we have more line contact or surface area that we can transmit torque and forces from one tooth to the other, okay? Additionally, you end up having more than one tooth engaged at any point in time. And the advantage of that is it's a quieter gear set. Up here, we only have one tooth in full engagement at any given moment in time. And what ends up happening is when they rotate relative to one another, the gears kind of hit one on the other. So a lot of times a spur gear set is considered a little bit noisier than a helical gear set because you still have engagement on the previous tooth as you're gaining engagement on the next tooth. So it literally is a quieter operation. The next one that we see here is a herringbone. Now this one's going to be harder to see on the screen here. So hopefully you can see it and you're looking in your book. But in this case, we've got real narrow teeth coming in at an angle about 45 degrees on one end, and then coming and meeting on the opposite side at the same angle, 45 degrees, where they meet in the middle here. And it looks like a herringbone pattern. The pinion would then also mesh or match up with that. Here again, we're going to have multiple teeth and engagement. It's a quieter gear set. It allows us to push more torque through for a low profile gear tooth. So usually the benefit here is you're going to have a wider gear, but the profile this way is going to be much shorter. Okay, and in some applications, it's needed. Over on the right side of that this is called a bevel gear. Now, the gear sets that we've seen previous here are the center lines of the input to the output are all parallel. Okay, you can see that here. On a bevel gear set, and then also on the miter gear set, which is down here, you're going to notice that the axes of the input to the output center lines are 90 degrees to one another. So a little bit different arrangement. Sometimes we need that. So in that case, you would consider one of those two types of gears. And then lastly, we have the worm gear set here. A worm gear set is going to be the spiral on what they call the worm, which would be, if you would kind of equate to our pinion. This is going to be the higher speed um, um, input, if you would, to then engage with the gear that's going to go around. Worm gears have some advantages of what we call zero backlash. So they're usually used for very precise applications where we are going to be moving, forward and back. Zero backlash just means that there's no, if you would, gap in engagement once you change direction. Okay. Worm gear sets are going to be more expensive because of that precision that they offer. So just kind of a glimpse at a number of different kinds of gears that you could see out in industry. But like I said, we're going to be focusing on a spur gear set like this, but we're going to find, even though we're only looking at one of about 8 different types of gear arrangements here, the principles and the foundation of gear kinematics crosses over in all of those. With a little bit of research and a little bit of digging, you can cross over quite easily. Okay, so those are different types of gears and gear sets. Let's go back to our PowerPoint presentation. Let's look at a little bit of terminology here. So my assumption when we start looking at gears is this is probably a relatively new concept to you. And if it's not, that's okay. But I know you've probably encountered gears along the way, but to kind of have the depth that we're going to be going and understanding the different features, we need to get ourselves familiar with some of the vocabulary. So I'm going to go underneath our camera here. And, as we physically saw some of those gears that were in engagement with one another, a couple of items are important to us, especially when we're laying out our design. And the first thing that we consider, or that we need to be aware of, is the physical size of these gears, okay? And one of the dimensions that we're always going to be looking at is, what is the center distance between, if we look down each one of these gears, what is the center distance between those center lines? So how far apart would the centers of each of the gears, so the pinion being the smaller gear and the larger one being the gear, so pinion and gear. That's going to be a big one. And the reason we want to find center distances is, as you can see here, it's the physical size. How much room are these going to take up? And then when we mount our gears, that center distance is going to be important because we have to accommodate that to be sure that we get appropriate engagement. Another dimension that is going to be something that we calculate for a gear or a set of gears is going to be what we call the pitch diameter. Okay. Now, I like this illustration because we kind of see some teeth engaged on both sides here. So the teeth are going to overlap, and you're going to notice that we have this center line diameter for each one of the gears. So for the pinion, the smaller one, and the gear, the larger one. And that pitch diameter, lowercase d as it's called, is where, if we position these appropriately on center, we would look here and we're going to notice that those two diameters are tangent to one another. They're the physical place where each one of these gears is going to engage push past each other, and all of the force and the rotational motion is actually going to move through that pitch diameter. Okay. So this also then kind of fully defines the extents or the physical size of each one of these gears. So center distance is from center to center, but then the pitch diameter gives us the bigger picture of how much space this is going to take up. So pitch diameter is going to be this diameter, what we call the tangential diameters or the effective diameters for when they're actually engaging with one another. Okay. Now, I'm going to kind of scooch back to page 262, and we're going to look down here. Now, with that kind of bigger picture of the two gears with their pitch diameters tangent to one another, we're going to look a little bit more closely at a couple of teeth on a gear. Now, this is a spur gear tooth profile, and you're going to notice that it takes this form that we have here. Now, when these are engaging one to the other, the tooth would come down of the mating gear into the space in between. And it's going to be the same profile, but just mirrored on the other side. Now, this is that pitch diameter circle. Okay, it's also called the pitch circle or the pitch diameter. Pitch diameter is going to be lowercase d. And when we're looking at English gears, obviously it's going to be measured in inches. Okay, so this is that pitch diameter that we were just looking at. You'll notice here that that is going to be about halfway up from what we call the root of the gear tooth and about halfway down from the top of the gear tooth. Not exactly, because when our tooth comes down in here, there has to be some clearance. It can't hit the bottom here. So the distance of the tooth above that pitch circle or that pitch diameter is called the addendum. That's over here, lowercase a. And the distance down below is the dedendum. Okay, and it's actually a lowercase b. I don't know why they don't use, well, they use d for pitch diameter. That's why they don't use d here. So again, the dedendum is going to be, if you would, deeper than the addendum because the addendum is going to fit down in here with that mating gear. Okay. The other thing that we're gonna hear a lot about on gears is called the face width. The face width is simply how deep that tooth is. And it gives us, if we kind of draw a line across there, that's the distance or the line for which a force from the mating gear is going to distribute its load or its force over. So the wider this gear, the longer that line, and the more force you can push in there, the more narrow it is, the less force and the more stress, if you would, is what that would see. When you are in the next class, which I believe is spring 1, you're going to be taking machine design elements. And in that class, you're going to be kind of finishing up the gear design where you're going to determine what is the face width and what are the materials. And you're going to notice that when you're calculating stresses for the forces that are generated, the wider that face width, the lower the stress because you're distributing that force over a longer distance. Okay. Let's go back to our PowerPoint and just see where we're at here, see what we've talked about. So we've talked about pitch diameter. We've talked about addendum, dedendum. We didn't talk about clearance, number of teeth, or circular pitch. So let's go back underneath. Circular pitch. Circular pitch is going to be the distance along the pitch diameter from one point on a gear tooth to the very same point on the next tooth. Okay. Clearance. Clearance is going to be the difference between the height of the addendum and the depth of the dedendum. Okay. So let me see here. On the next page, on page 264, you're going to notice this would be the bottom of the tooth. As the top tooth comes in on that pitch diameter, okay, where they engage, you're going to notice that the top of the tooth is going to hang down into what would be the bottom of the tooth on the tooth on the gear that's engaged with. This distance right here is the clearance. Okay. We have to have clearance between what would be the addendum and what would be the dedendum for the mating gear. Otherwise, if these touch, that's a problem. We've got interference and they would not, the gears wouldn't last very long. Okay. So clearance is an intentional amount of exactly that clearance so that the addendum and the dedendum don't interfere with one another. We talked about circular pitch. Oh, and number of teeth. The number of teeth is simply going to be physically counting around the perimeter of the gear or the pinion, how many teeth are on there. Okay. And you're going to notice here that we call that out with the letter, a capital letter N. Um, and then diametral pitch. Diametral pitch. If we go back over here, diametral pitch, we're going to look at page 263, the top of page 263. At the top here, this is a chart that gives us a nice illustration of the comparison of the different sizes of gears or gear teeth. Now, you'll notice that each one of these gear teeth has a number associated with it. The larger the number, okay, the larger the number, the smaller the teeth. The smaller the number, the larger the teeth. So when we get into this bottom row here, these are considered kind of big, chunky, if you would, teeth that we would expect for the application to be more volatile or to push more force and such through, okay? In the middle here, there's a kind of like middle of the road applications. And then up on the top here, these are going to be more delicate, smaller applications. Now, although these probably aren't as small, but you can kind of consider these as like maybe printer gears, you know, that you might have like an inkjet printer gears to pull paper through are going to be smaller gears like this. Middle of the road applications, like I'm going to say 5, 6s, 8s, 10s, 12s, these guys right here, these are going to be like machinery applications. And then these larger ones are going to be like machine tools. Okay. So applications where we're going to see, you know, bigger forces, more volatile, you know, type of environment would be the bigger teeth. Okay. Now, as we look down here, and before we move on, this is then going to be standard tooth sizes. Now, to identify these tooth sizes with these numbers are referred to as diametral pitch. Diametral pitch. So, pitch diameter, lowercase d, is the physical, numerical size of the diameter that we mesh with the other gear. So as we saw a couple pages down the way here on page 273, pitch diameter is here. Okay, pitch diameter as it goes around. That's a physical size, and that's lowercase d, pitch diameter. Diametral pitch sounds very similar, but this refers to the size of the tooth, and it's given in a number. Notice that not all numbers are going to be a diametral pitch. So for instance, they go 3, 4, 5, 6, skip 7, then they go to 8, skip 9, go to 10, skip 11, go to 12, then they skip a bunch and they go to 16. So these are standard sizes, okay? So if you're a gear manufacturer, you're going to be making the gears to these sizes, kind of like when we're a fastener manufacturer, there are standard sizes of fasteners. This is the same thing with gears, okay? Now you could make them in between, but they're not going to be the ones that you can, like, if you would, you know, go to a catalog and pick out a number 8 diametral pitch gear. Now, the key to this, as you can imagine, is if you have two gears that are enmeshed with one another, they have to have the same diametral pitch, okay? So again, pitch diameter, they don't have to be the same. Let me go to the pitch diameter. Pitch diameter, I can have more teeth for a bigger diameter, pitch diameter, smaller pitch diameter, less teeth. But the teeth, so that they mesh appropriately, have to be the same size, and that's called diametral pitch. Okay, so pitch diameter is the big circle with a small d or a lowercase d. Diametral pitch is the size of the tooth. Okay, size of the tooth. Now, to calculate the diametral pitch, we're going to use this equation right here. Okay, and that's capital P sub d is equal to the number of teeth divided by the pitch diameter. Okay, so what I want to do is I want to start us with, there's not going to be a ton of calculations, but we're going to add to this as we go through, and it'll be a nice place to have um, an equation sheet so that you don't have to try to page through the chapter to try to find the things that you need. So what I'm going to do is I'm going to encourage you to create a gear equations sheet. And oh, by the way, you will be handing this in with your practice problems. So might as well make it along with me now. And our first equation is going to be for diametral pitch. It's capital P sub D. So this is one variable. It's going to be equal to capital N number of teeth divided by lowercase d. Okay. Now, I'm just going to go like this, and I'm going to put the units for each one. Capital N is the number of teeth, as we said. So if there's 10 teeth, the units for that quantity are going to be teeth on the top. And then pitch diameter is going to be in inches. So the units for diametral pitch are going to be teeth per inch. Now, when we're given diametral pitch or we're specifying diametral pitch, they're just going to give us a number. They're going to say a number 6 gear, and that just means that's the diametral pitch. So you're going to have to kind of get used to how it's being specified. And we'll see that in the descriptions. And as we use this more and more, you'll get more and more familiar. So over on the left-hand side here, I'm going to say capital P sub D is equal to, this is called diametral pitch of a gear. And I like to put in parentheses, size of tooth. Okay. Size of tooth. And the units here are teeth per inch. Even though they're not going to be giving in a problem, we're going to see that when we work problems where we either have to use the diametral pitch or calculate it, we're going to have to add the units when we kind of use it in a problem. N is going to be the number of teeth. And those units are going to be teeth. Very simple. Okay. And then lowercase d is going to be pitch diameter. And that is going to be in inches. Okay. So kind of the start, and then we'll continue to add here as we come up with, come upon other equations that we're going to want to add. Okay. So diametral pitch is going to be the size of the tooth. It's going to be a number, an integer number, and its units are teeth per inch. Okay. All right. Let me go back to our PowerPoint. So we covered all those items. And the last item that we have here is pressure angle. Okay, pressure angle. So pressure angle, we're going to look on page 264, right here. We kind of identified this where we showed how when the two teeth come together, the addendum, the top of the tooth, kind of sneaks down into the bottom of the tooth, which is called the dedendum, and then that difference is going to be our clearance. Now, as we know, where they come together and they hit one another, this is the pitch circle, the pitch diameter, okay, for the bottom gear, and then the pitch diameter for the upper gear. Okay, so that's where everything comes together. Now, there are two other circles that can be generated from the geometry. I'm not going to get into the weeds on how to calculate it, but there's a base circle for one gear and a base circle for the gear that it's engaged with. If we take a line and we go from one base circle tangent through the pitch diameter point where they engage, and then tangent to the bottom base circle, this angle of that line that it makes to horizontal is called the pressure angle. Okay, the pressure angle. Now, not only do gear teeth have to be the same diametral pitch, same size tooth, they also have to have the same pressure angle. Now, there are 3 pressure angles that you will see gear specified to. The most common for industrial applications, such as like in machine design, are going to be 20-degree pressure angles. This is where we most often will always start with our gear design. We're going to say, we're going to, probably start with a 20-degree pressure angle. Okay. Now, the other one that we can specify to brand new gears is going to be 25. And you'll notice that the profile of the gear tooth is a little bit different. Okay. And we'll talk about how it changes from one gear to another in just a bit. But then there's a third one, the one over on the left here. This is a 14.5-degree pressure angle. Now, if I have a 20-degree pressure angle, I cannot use any one of the other pressure angles with it. So when I have two gears that are in mesh, they have to have the same diametral pitch, same size tooth, and the same pressure angle. Okay. I can't put a 14.5 with a 20 or a 25 with a 20. Okay. Now, why are there three? Okay. So let's first look at, and I'm gonna actually go on my back side here. I'm gonna draw out a pressure angle example or thing here. So if I look at a tooth and I come across, this is my point of engagement, okay, from one tooth to the other. So I'm really kind of mimicking, if you would, that middle point where they would hit one another. This is where the force is being transmitted from one gear to another. Okay. Now, along that pressure angle, see, I should have a straight edge here, but I don't. Along that pressure angle, okay, so this is my 20-degree pressure angle. About that force is coming in. Okay, this force is coming in from one tooth to the other. Okay, and I'm just going to show it going down and to the left. Okay, along that 20-degree pressure angle. Now, for those of you, actually all of you probably have had statics along the way here. We know that we can break that force into its X and Y components. So if I come over here at that 20-degree pressure angle, I'm going to have a Y component, right? So we usually call this the normal force. That's going to be the normal force. Now, in kinematics, we are not talking forces. So don't worry, we're not going anywhere with this. But when you get into machine design elements, you'll hear this again. That's when you start working in forces. But I think it's really important to just kind of show you this force stuff for just a moment because it helps to, I think, identify when and why you would use these different pressure angles. And using the same thing for the X component, which is what we would call the tangential force, okay, would then come in along that line. Now, as we can see here, if we would place our force going down normal and tangential with our resultant force coming in at an angle, okay, if we would place those here, you can see that on a tooth like this, it is going to push this down towards the center of the tooth where we usually have more material. Okay, so that goes down. The one that is usually the bigger problem, the force that's the problem, is the tangential force. The tangential force, if it's coming in at an angle like this, it's wanting to push that tooth over. And so what can happen is two things. Number one, it's always going to hit on that surface, so it's going to cause pitting, okay, or cracking on that surface because it's hitting on there. So over time, it can cause fatigue on the surface and kind of break it away. But another thing that it can do is if this gets too high of a force, it's going to like bend that tooth over. It can actually shear it off. Okay, that can happen with gear teeth, as we know. So that tangential force is the one that usually dictates our design. Okay, now let's say we move this up to a 25-degree pressure angle. So from horizontal, we use that same force. I'm going to kind of exaggerate this, but let's say I do this. I've got now a resultant force coming in here. What happens is my normal force is going to get larger, right? You can see that. So this goes up, 20 to 25 degrees. So this goes at 25 degrees from here, from horizontal up. But then what happens is it's if I go down here, my tangential gets shorter. Okay. So that's why if I know I have large forces that are coming in, I want to push as much of that Y component down towards the center of the gear where there's more material and minimize the amount of tangential force that would um, impact that tooth when it hits on each other, but then also so it doesn't like move it to bend it over or shear it off. Okay. So 25%, or I'm sorry, 25-degree pressure angles are going to be for applications where we're going to see higher forces. Okay. 14 and a half. If I move this down to 14 and a half, something like this, same force, look what happens here. This time now at 14 and a half, my tangential force is going to get longer. So now I have an increased force along that horizontal axis, which is going to increase the amount of pitting or the sooner I'm going to get pitting. And it also increases the risk of shearing off that gear tooth. And then I'm minimizing or making smaller, pushing material down to where there's naturally, or I'm sorry, pushing force down naturally where there's more material. So as you can imagine, the 14.5-degree pressure angle, there was a lot more failures on those gear teeth. So they just started saying, okay, we're just not going to make them anymore for new designs. It's not that they're not valid. It's just that we're only going to do replacement parts or things that are already out there that we need to, improve upon or we need to change out. We'll keep them at 14 and a halves, but any new designs are going to be 20 or 25 degree for exactly those reasons that we talked about. So again, you're not going to be calculating any forces in this class, but I think that's valuable to kind of know and understand how that pressure angle changes the forces that come in. So you can kind of see why you would use one over another or why 14 and a halves kind of left the scene. So questions about pressure angle or the items that we have here right now. Okay. Probably the biggest thing is just keeping track of pitch diameter versus diametral pitch. Diametral pitch, capital P, is going to be the size of the tooth. Pitch diameter is that diameter that's going to be tangent from one gear to the other, showing where they engage. Okay. Involute tooth profile. So that is going to be the profile. Let's see here. I think it's right here that we see down here. So this is the natural tooth profile that is created for spur gears. So that's what the tooth profile looks like. So it's specific to spur gears. So let's look at an example and we'll do this one together. Now, we're just going to do the first part of this and I'll explain why. So for example 10.1, where this is going to be your first practice problem. So what I want you to do is get out a sheet of paper and we are going to work this problem together. So for this problem, it says that we have a 20-degree full depth involute spur gear tooth. And a lot of times you don't even hear somebody say involute spur gear. It's just a spur gear because they're all involute. Okay, so that's a specific profile on the outside of the tooth. It has 35 teeth, so that's going to be our N, capital N, has a diametral pitch of 10, okay? And that's going to be our P sub D. They want us to determine the diameter of the pitch circle or the pitch diameter. And then it says also the circular pitch and the base circle. Now, we're not going to do the circular pitch and the base circle because you'll never be asked to do that, okay? Years ago, when we would draw manually, whether it was maybe in AutoCAD where we had to create all the features and maybe draw the profile. Now with the software is more sophisticated and smarter, we can actually have the CAD software generate the tooth profiles, which these would be part of that. So the only thing that I want us to find is, and it's going to come in handy in not only your assignment, but in different calculations that you would do typically for gear drives, is just the pitch diameter here. Okay. So what I'm going to do is I am going to start my example here by just saying, okay, this is example 10.1. And we want to identify the items that we are given in this problem and then what we need to find. So given, okay, we're given the number of teeth. So N is going to be equal to 35 teeth. Okay. And then we're also given the diametral pitch. So diametral pitch size of the tooth is equal to 10. Okay. Now, in our problem, it just gives the number 10. And that's how we're going to find that we're given the pitch, the diametral pitch of a gear. Okay. The size of the tooth. It doesn't give any units with it, but from our equation sheet, we know that diametral pitch, when it's calculated, its units are actually teeth per inch. So we're going to want to add teeth per inch, even though they're not given, but we need to add them so that in our calculations, we're going to get the right units. Okay. So we're given those two quantities for this problem, and then we want to find the pitch diameter. Okay. So that's what we want to find is the pitch diameter. Okay. And I'm just going to go like this. You don't have to add this, but just so that we know we're early on, this is pitch diameter is what we want to find. And just as a contrast here, the pitch diameter of the gear is going to be on page 273. It's this diameter right here, okay, for this gear. So the teeth are going to be engaged in the middle. The size of the tooth is that diametral pitch, but pitch diameter, lowercase d, is going to be what we want to find, the physical effective diameter for these, where they're going to mesh, where they're going to be tangent to one another, okay? So to do that, we know that our equation is diametral pitch is equal to number of teeth over pitch diameter. So that's our base equation. So diametral pitch is equal to number of teeth divided by pitch diameter. Now we're given diametral pitch. Okay, that's the 10. We're given the number of teeth. That's the 35 teeth. We need to find D. Okay, so I just want to rearrange this to solve for D. So I'm going to multiply D up, pitch diameter, and pull the diametral pitch down below. So my D is going to be equal to the number of teeth divided by the diametral pitch. Does everybody see that? Okay. So I just multiplied both sides by lowercase d and then divided both sides by P sub D, or diametral pitch. And then I'm going to say equal to, so then this is the number of teeth. So up here, we've got 35 teeth divided by 10, and you have to put your units in here. The 10, I'm sorry, yeah, 10 teeth per inch, which is the diametral pitch. Now, because I have my units here, I'm going to cancel out from top to bottom. So you'll notice here that I have canceling out the teeth. Okay. Now our inches are in the denominator of our equation. So that means that it multiplies up on top. So the units here are inches, which we are expecting for a diameter, right? So for our pitch diameter, we're expecting inches. So if we solve here, 35 divided by 10, we're going to get 3.5 inches is our pitch diameter. Okay. So again, our pitch diameter is going to be, if here's the center of rotation for our gear, it's this diameter right here. And it's the diameter that's going to be tangent and engage with the mating gear. Okay. So pitch diameter. Any questions about example 10.1 right now? So you want to make sure that you tell me what you're given with units, what you're going to find, your equation in variable form, rearrange it for your unknown variable, put your values in with units, cancel out. Don't just put teeth and teeth per inch and then just magically have inches appear. I want to see that you notice that there was a cancellation. So you have to cancel out things, in this case, top to bottom, the teeth, so that you're left with inches in your final units. Also, do not just put a box around 3.5 inches. If it's asking for what is the pitch diameter, I want the variable equal to its final number. Okay, so I'm looking for, if you look at, okay, we need to find the pitch diameter, should be that variable, lowercase d is equal to its number with the inches. Okay, so this is our first practice problem. Any questions at all? Okay, all right. Then let's go back to our PowerPoint presentation and continue on. Standard gears. So there is, as we said earlier, there is going to be um, sizes that are diametral. I'm sorry. There are going to be common gear teeth sizes, their diametral pitch from gear manufacturer to gear manufacturer. And we already saw the different sizes at the top of page 263. So we looked at these, right? Now, if I go to, for instance, a gear manufacturer like Falk or um, Browning or Rush Gears, those are three popular ones that you can buy industrial gears from. They're all going to have, if you would, a standard set of gears. Just like I said earlier, just like when we have fasteners. If I have a fastener manufacturer, they're all making the same ones and they're made to the same specifications. Now, those specifications, if we look at page 266, down here in table 10.3, these are the American Gear Manufacturing Association. They're like the governing body, if you would, of the specifications for the standard gears, okay? And you'll notice here that for some of those items that we talked about, addendum, dedendum, which is the distance above and below the pitch circle, these are going to be the calculations for those physical sizes. Okay. So notice that they're dependent on their diametral pitch. Okay. So you're going to notice diametral pitch in each one of these equations. We don't go through and generate the tooth profile because CAD softwares do it now for us. And you don't have to manually draw them. But know that these are the physical sizes and the physical dimensions based on the diametral pitch for each one of these, uh, uh, characteristics of the profile of a gear tooth. So that chart is there for you. Relationships of gears in a mesh, center distance. So as we identified earlier, center distance is going to be one of those things that we're very interested in, only because as designers, we've got to lay this out and make sure that things fit properly. And we have to figure out where are we going to mount things. So going back to this very same illustration here, not only do we want to know what the physical size of the pitch diameters are, but how far apart are those? So when I do mount those, they mesh properly. So capital C is going to be our variable for center distance. Now, the equations for center distance are going to be at the top of page 268. Okay. Now, depending on the information that we're given, we can calculate this a couple different ways. So we're going to use these two equations here. Now, these are for external gears only, and that's all we're going to be dealing with. That's, again, the most common type of gears that we deal with. So if I go back to my gear equations sheet here, okay, I'm going to add to it my center distance equation. So C is going to be equal to, and we're going to notice that we can take R1 plus R2. Okay, R1 plus R2. R1, the number one, is always going to refer to the smaller gear in a set, okay, which is called the pinion. And then 2 is going to be the larger gear or the gear in a set of gears that are meshed. Okay, so 1 is the pinion, 2 is the gear. We can also say that's going to be equal to the pitch diameter of the pinion plus the pitch diameter of the gear, and we're going to divide that by 2. Okay, now, as we look here, C is equal to center distance. Okay. And the units are going to be in inches. Okay. And then D is pitch diameter. All right. But R is going to be, I'm going to say pitch radius, which is half of the diameter. Okay. And that's going to be in inches as well. Okay. Now, another way that we can calculate it, because we know if we rearrange this diameter, pitch diameter is going to be equal to number of teeth divided by diametral pitch. They do that rearrangement here. So if we go back underneath, using that relationship, we can also use the number of teeth and the diametral pitch. So if I look here, I can say C is going to be equal to the number of teeth on the pinion plus the number of teeth on the gear divided by 2 times the diametral pitch. Now, for these two gears, pinion and gear, to be in engagement, they have to have the same diametral pitch. So number of teeth, capital N, of our pinion, number of teeth of our gear, add those two together and divide by the diametral pitch of that set times 2. Okay. So those are the two options that we have for center distance. Okay. And again, depending on the information that you have in a problem, one is going to probably be more efficient, if you would, than the other. So let's go ahead and look at example 10.3. Now it says we want to determine the center distance between the pinion and the gear on a concrete mixer. So we'll look at that in just a little bit. So what we're going to kind of do is go through this process, and we want to identify what variables are we given, what do we need to calculate or find, and then we're going to look at our equation sheet, like what are the equations that we're going to be interested in using, and then we're going to kind of work through this in the steps. So on page 268, we are going to find example 10.3. Okay, example 10.3. And here we have two 5-pitch 20-degree full depth gears are used in a small construction site concrete mixer. Okay. The gears transmit power from a small engine to a mixing drum. All right. So here's the engine right here. We have a shaft coming off of it, and we have a small drive gear attached. Okay. It engages with a larger driven gear. So the driver is what we would consider our input. So this is driving or putting the motion into the system. Okay. So this is the driver. Then it's engaging with the driven machine, which is going to be the concrete mixer. Okay, and it's going to then rotate this drum around. And as you can imagine, this is going at a higher speed. So this is going to be rotating around, and it's going to slow it down so that it can then rotate that drum, which is probably going to be quite heavy, right? Because of the concrete that's on the inside. Now this gear transmits power from that small engine to the mixing drum. Sorry. This machine is shown down here. The pinion has 15 teeth and the gear has 30 teeth. Determine the center distance. Okay, so let's look at what we're given here by just kind of pointing to the numbers to start off with. So first of all, determine the center distance. That's going to be C, right? And that's what we're going to want to find. Okay. Here you're going to notice that the pinion has 15 teeth. So this is going to be capital N sub 1. Okay, because 1 is our pinion or our smaller gear that's in engagement. And then the gear has 30 teeth. That's going to be N sub 2. Okay. And then up at the top here, you're going to notice that it says 2-5 pitch. It doesn't say the diametral pitch is, but when we see just a number, an integer number, 5 pitch, this is going to be our diametral pitch for each one of the gears, because they have to be the same number for them to be able to properly engage. Okay. So what we're going to do here is we're going to, grab our practice problem sheet. So I'm just going to go down below example 10.1, and this is going to be example. This is 10.3. And I am given the following. Diametral pitch is equal to 5. Okay, now remember, it didn't give us any units in the problem, and it won't. But we know that the units for diametral pitch are teeth per inch. So we want to add that here because we want to make sure that we include those in our equation. Number of teeth on the pinion was 15 teeth, and number of teeth on the gear was 30 teeth. Okay. And what we need to find is our center distance, right? Center distance. Okay. So as we look at our equation sheet to find the center distance, we had two equations, these two equations, right? We had pitch diameters, radiuses, or number of teeth and diametral pitch. Which one, based on the information that we're given, do you think we should use? The first one or the second one?
The second one.
Yeah, the second one. Why are you picking the second one?
Because we have those variables, we're not going to need to like convert them.
Yes, exactly. So you're going to notice that we're given number of teeth for each and the diametral pitch, which the second equation lends itself well to that, right? Okay. So what we're going to do is we're going to say, okay, C is equal to N1 plus N2 divided by 2 times the diametral pitch. Okay. So that's going to be equal to 15 teeth plus 30 teeth divided by 2 times 5, and we want to put the units in there, teeth per inch. Okay. Now on top, these are going to combine, right? These are going to combine, and I'm going to just kind of put out here. You don't have to do the extra step, but I just want to show you units wise so we can see the cancellation. We're going to have 15 plus 30. That's going to be 45 teeth divided by 2 times 5, which is 10 teeth per inch. Okay. So my teeth are going to cancel. I'm going to have inches in the denominator of the denominator, so they multiply on top. So my center distance is going to be 4.5 inches, right? So a couple things here. As we look, make sure that you put your box around your final answer. Make sure that you're answering the question. If we want to find C, I'm seeing C equal to, and its value in this case 4.5, and then its units. Make sure that when I look at this and you have your units in place here, you cancel out so I can see the final units, are resolved. That's exactly what it is. That it also gives you again that clarity, that confidence that you set it up correctly if the units come out correctly. Okay. Make sure that you identify your givens, what you're going to find, and then it's easy to read. So any questions on this example 10.3? Okay. It's our second problem. We will be looking next at section 10.7, but before we look here, why don't we take our break and then when we come back, we'll continue on here and then do a couple more examples. So I am going to stop our recording.